Thank you. So to summarize this very long title, what we were essentially interested in is if you give someone an assistive device, what does that do to the underlying muscle function for the muscles that it's trying to actually assist? And the motivation for this really is when we look at bouncing gaits, they're very useful because we can store and return energy in series elastic structures such as tendons. That's one of the benefits. And several people have designed very nice exoskeletons based on this principle or inspired by this principle. So we can see the Farris et al. Ankle exoskeleton there, and Gregory and Pensacola full leg exoskeleton, which use passive springs to store and return energy. And they've done a pretty nice job of what they were setting out to achieve. So in the case of the Farris et al. Ankle exoskeleton, they managed to reduce plantar flexor muscle activation. That's great. They were both also able to reduce the biological contribution to leg or ankle stiffness. So we're loading the biological tissues less, which is great. And a benefit of this is that they were able to reduce the metabolic power requirements of these movements. So this all seems great, but we then need to think about, or I think we need to think about, how this comes full cycle and what that then does to the normal interaction between muscle and tendon. Because not only is it great that we can store and return energy in elastic structures, but that has a second benefit, that it allows the muscles themselves to operate relatively isometrically, which for those who are not so familiar with muscle mechanics and physiology is a really good thing, because it's the most efficient way for a muscle to produce force if it's not changing length very much. So we wanted to ask the question, how does giving assistance with a spring-loaded ankle exoskeleton affect the underlying muscle mechanics? In this case, we were focusing on Soleus. So first we needed an exoskeleton, so a very similar design to the Farris et al. Exoskeleton with, you can see here, a spring to assist plantar flexion. And we asked people to hop in these exoskeletons, as you can see here. And while we were doing this, we collected motion capture for kinematics. We got ground reaction forces so that we could do an inverse dynamics analysis to get net muscle moments or net joint moments, and EMG to have a look at muscle activation. But what I really want to get into, we also have a load cell here to measure the contribution of the spring to the moments. What I really want to get into, and what we were really doing that was novel here, was using ultrasound imaging to look at the muscle phasical behaviors. So what you can see here is an ultrasound image. So we put our ultrasound probe to get a longitudinal slice through the calf. So what you can see here in the image, this is the skin right at the top. We're going deeper into the leg here. This is towards the ankle, and this is towards the knee. And this V-shaped structure you see here, that is the distal end of the medial gastrocnemius. And underneath it here, we have Soleus. So here are the two aponeuroses, the borders of Soleus. And hopefully you can see a dark and light banded structure running through the muscles. And those are muscle fascicles, or bands of muscle fascicles and parallel elastic tissues. And so we can measure the length of a fascicle in any image, and we can get the pronation angle too. And we collect those as videos. So we're able to record muscle fascicle lengths throughout the movement. So some of the data that we've got out so far, so we were hopping in this case at 2.5 hertz, and you can see we had two conditions. We had them wearing the exoskeleton and a control condition where they didn't have any assistance. We can see in terms of Soleus EMG, reductions in activation, particularly just before landing. So here we're going from landing through to the next landing, with the dotted line is always going to be the start of the aerial phase. So we've got some reductions in activation, and that resulted in a reduction in our estimate of Soleus muscle force. So here we've got forces in the control in red and with the assistance in blue. So we can see almost a 30% reduction in muscle force. Not surprising if we've got a reduction in activation. But the other thing that we did have was an increase in the excursion of the fascicle. So you remember I said that the muscle fascicle being isometric, not changing length much, was good. Well, now we're actually seeing an increase in muscle fascicle length when we're giving the assistance. And the result of this is actually that the average power provided by the fascicle is about the same in both conditions. So we're actually not really reducing the work that the muscle, the contractile element of the muscle itself is doing. The other side effect of lesser force is that we're able to stretch and recoil the tendon less. So when we have the assistance, we can see we have a reduction in the amount of energy we're able to cycle in our series elastic element, or our Achilles tendon, essentially. And what we end up with then, if we break that down into the total, if we break the total power output of the muscle tendon unit down, we see that when we use an exoskeleton, the fascicle is responsible for a greater proportion of the positive power that is provided. So I would argue that this is not a good thing. It's much better for our efficiency if we have more power output cycled in the tendon rather than actually asking the muscle fascicles, the active component, to do work. Which led to some conclusions. So Soleus fascicles go through a greater excursion with an exoskeleton. Because of a trade-off between the force and the length change, we have the same power output in both conditions. And the lesser forces mean less energy cycling in elastic structures. And this potentially could make the muscle itself less efficient, not necessarily the whole movement. That's not what I'm saying here. I'd like to acknowledge Ben Robertson and Bruce Wiggin, who are both talking this week, for their help with this study as well. Thank you. Okay, so to get an estimate of force in Soleus, we took the net ankle moment and divided it by the moment arm to get a force in the tendon, and then we corrected that for pronation angle. We split up that total force based on the relative cross-sectional area, physiological cross-sectional area of Soleus, so about 60 or 70% of the total tendon force is attributed to Soleus. And we then correct that for pronation angle.
I think there was a speaker here first. So. Yeah.
Okay. So you've shown, in a sense, this is another example of what I think is coming to be a truth, that it's really, really hard to make the body, to help the body do anything it's already good at. But that's not the same as saying this is a useless idea, because there are things the body's not good at, and things you'd like to do more of that you can't do yet. How would you extrapolate your results to cases like hopping with more weight, or hopping faster, quicker, different, anything different that this might be helpful for?
Well, so I suppose what we have here is if you're adding demand to the task, for example, if you were adding weight, you might be increasing the total amount of, let's say, force or the total ankle moment that has to be produced. And so if you could get the proportions or the proportion of that that's coming from the exoskeleton, right, I would assume you could maintain a normal function in the muscle, or normal, in inverted commas, function in the muscle. So if you could, essentially what I'm saying is if the added demand was matched by the contribution from the exoskeleton, potentially the muscle fascicles or the muscle tendon unit contribution could be the same. I'd also like to say that, as I hinted at the end there, although it may be making the muscle tendon unit slightly less efficient, the metabolic data that we have that goes with this suggests that you are still getting a reduction in metabolic cost when you hop with the exoskeleton. So it's not that we're not getting any benefits from the device. It is that maybe we could get more, or maybe not.
Okay, there in the back. What was your definition of a hop?
So it was essentially bilateral hopping with an aerial phase. They were kept to a metronome, so you had to land on the beat of the metronome. Here I showed 2.5 hertz. We have data for other frequencies as well that I didn't show.
Did their feet leave the ground?
Yes, so there was an aerial phase. That was the vertical line on the graph showed the start of the aerial phase during the hop. So it's not a bounce.
Unfortunately, the time is